I'm going to talk about quantum gravity on manifold with boundaries, Schrödinger evolution, and constraints. I will explain what is the meaning of Schrödinger evolution. This is a work I've been working on for a year, and my motivation is to study the black hole evaporation. And you know that in quantum gravity, there is no time evolution. In ordinary quantum gravity or canonical quantum gravity, there is no time evolution. And this is a problem if we want to study the evaporation of a black hole, because the idea of the evaporation is that you fix the initial conditions and you want to see how this initial condition evolves to a final condition. But if there is no time, how you evolve this initial state, no? There are several ideas or proposals to study this. One of them, the reasons is the what's the name? Sorry, the wormhole, the replica wormhole, to study the page curve. This is really is not conclusive from my point of view, let me say, because of in the end, to be sure that the evolution is unitary, as we expect, what we have to compute is the transition amplitude between the initial and final state, and not the Hawking page, the Hawking curve, sorry. So first, I'm going to present.
Can you explain why there is no time
in quantum gravity?
Yes.
This is a problem, or not a problem. This is a feature from all the theories that are diff invariant. All the theories that are diffeomorphic invariant, there is no time, because all the variables or the dimension of, for instance, in 4D gravity, time and space are at the same footing. So you can find the same problem in string theory, for instance. In string theory, there is no time.
Like in usual QFT, right? It's Lorentz invariant.
It's Lorentz invariant, but not diff invariant.
But what's the difference?
Like general covariance. You know, you can take any coordinate and you can go from any coordinate system. But in usual quantum field theory on flat space, where the background is fixed, or the background is flat, the only transformation you are allowed to do are the rotation, the Lorentz rotation.
Yeah, but like there you still have to choose time, right? That superficially it breaks Lorentz invariance, but eventually the theory.
This is what I'm going to do here. Actually, in canonical quantum gravity, you have to choose some time by doing a foliation, but in the end, you will see that you have no evolution. There is no evolution with respect to this time, or any time you choose.
Thank you.
Okay. Yes. This is what I'm going to do. Not exactly asymptotic time, no, but the time at the boundary. And then you can take the boundary to infinity if you want. But for introducing time in quantum gravity, you have to put the gravity system in a manifold with a boundary, with a spatial boundary. Otherwise, there is no time. And you will see why, no? Because at the boundary, you fix some of the degrees of freedom. And this fixing is what induces time. Because in the bulk, nothing is fixed. No? This is why there is no time. Okay, I'm going to introduce first the Einstein axiom, and can I move this? how can I, where? Doing, I see. Okay. Okay. The idea is to consider this kind of manifolds with two space-like boundaries and one time-like boundary. Then, if you want, you can take the boundary to infinity, you know, and consider asymptotically something, space-time, flat or whatever. Maybe you are used or you are familiar with these two terms, or this term, which is the given Hawking's term. However, when you put the gravity in this kind of manifold at the junctions between this boundary and this boundary, you have to introduce this term. And this is because, for instance, this case, which is the extrinsic curvature of the boundary, depends on the normal vector. And when the boundary has this jump here, the normal also jumps, and there is no, it's not continuous. No. Yes, this is. Yes, I'm going to explain. I'm going to explain in the next slides. Yeah, I forgot to tell you. Actually, I told you that I'm going to explain what is the Schrödinger evolution, and the meaning of the Schrödinger evolution is that we are going to evolve the states in space-time with Lorentzian signature. Otherwise, there is not Schrödinger evolution. And this is why we need these two boundaries, when you can fix the initial and the final state. This is ordinary, this is what you do in ordinary quantum field theory. So you need to introduce this term at the junctions. And this term is usually is called the Hayward term. And it depends on the normals, the unitary normal vectors of the boundaries. This one and this one is the product of these two normal vectors. For getting this term, you have to work out the variation of the Einstein Hilbert action in this kind of manifold. It's a job, very hard job, but you find that you need this term in order to have a well-defined variation problem. Yes. You don't get the Einstein equation, because when you do the variation, sorry. If you are working on this manifold, this kind of manifold, and you don't add this term, in the end you will have an extra term in the variation. Exactly like this, with the opposite sign. See the variation. This is the variation of the Einstein Hilbert action on this manifold, and you see that there is no eta term in this. And the boundary condition we're using is that we fix only the induced metric on the boundary, the three metrics on the boundaries, which are these ones. This is the boundary, the induced metric at the spatial manifold, the spatial boundary, and this one is the space-time, the space-like. So without this term, you get an extra term here, and you cannot say that this is zero. So by fixing this, by fixing these two, so these two terms, and you can forget about them, and you get the Einstein equation. this one, the vacuum, because I'm not considering matter. So, any question so far? For doing quantum gravity or canonical quantum gravity, we have to use the ADM formulation of gravity. For that, instead of using the metric, the usual way, the 10 components, you use this parametrization of the metric, this one here. This is the ADM parametrization of the metric. In particular, at the constant slice, at the constant time slice, the metric is this one. So you don't have this term, you don't have these two terms, and you get only this. As we are considering also spatial boundary, you can also introduce another foliation. Foliation not of the space-time, but of the particular slice, using this parametrization here. Before continuing, let me do the counting of the degrees of freedom. No? There are 10 components in 4 dimensions. 1, 2, 3, and 6 coming from the 3 metric. These are 10. The same here. No? Now, similar here. No? For the 3 metric, I have 1, 2, 3, and 3 more, 6. This is a symmetric 2 by 2 matrix. So we want to impose the boundary conditions that the 3 metric will be fixed at the boundaries. So first, we have to fix at the boundaries, at the space-time, space-like boundaries. We have to fix all these degrees of freedom, or HAB. But what happened at the spatial boundary? This is a parametrization of this. This is the metric. It's like, for instance, in spherical coordinates, this will be something like R IJ. For instance, in spherical coordinates, forgetting about all these degrees of freedom, you can forget about this. These are the angles of the sphere. And here you have 1, and here you have R squared. So yes, with this parametrization, what we are saying is that we are using a coordinate system such that the boundary is at the constant R. It's not a spherical coordinate, but I can use this without. It's like a radial coordinate, but it's not the radial of the spherical coordinate. No, it's a radial coordinate. And each constant R give you a particular slice of this. So the question is, what happened at the boundary, at the spatial boundary? So when you work out the full metric, now you have to evaluate this metric with this parametrization at a constant R, which again, you can take this R to infinity in the end of the calculation. When you do this, you find that at the constant R, this is the metric, and you want to fix this metric at the boundary. This is the 3 metric, but this 3 metric at the spatial boundary. Remember, we already fixed the spatial metric at the time boundary. Let me say like this, which are these degrees of freedom. We fixed these degrees of freedom and these 2 boundaries, and now we have to fix the 3 metric at the spatial boundary. Then you find that for this you have to fix in this particular parametrization, the ADM parametrization, you have to fix this combination and this combination. So you have to fix this, and you have to fix this at the boundary. Some example, for instance, again, in spherical coordinate, at the constant r, what you are doing is you are fixing the metric, this metric at the sphere. So you have to, in this, with this parametrization, you have to fix this combination and this combination. So these two combinations are given. You give this as an input, or you can rewrite this like this. No, this is completely fixed at the spatial boundary. Let's see what is happening here, no? Because usually we consider that in the ADM without boundaries, these degrees of freedom, the lapse and the shift function, they are independent. However, when you put the theory on this kind of manifold, now they are not independent. They are related. They are related by these conditions. And this is important when you want to do the variation, when you want to take, when you want to find the equation of motion, because now you cannot freely take the variation of these degrees of freedom, for instance, no? Because they are related. You understand this part, no? Everywhere. Only at the boundary. This is what this is. So they are independent in the bulk, but they are related at the boundary. No constant is given, no? You fix the, it's not constant. Yeah, this could be any function. Compatible, of course, with the equation or the solution, but they can be any function. So, summarizing, you have that the metric, now you can decompose the metric in the ADM form in these degrees of freedom. If you count these degrees of freedom, you find that there are 10 degrees of freedom. But at the space-time, and the space-like boundaries, you fix these 6 degrees of freedom, and at the spatial boundary, you fix these degrees of freedom. They are different. You are fixing different degrees of freedom, but still these are 6. 1, 2, 3, and 3 more 6. 1, 2, 3, and 3 more 6. And 4 remains unfixed. And these 4 degrees of freedom are the ones that lead to the constraints in the ADM formalisms, no? Usually in the lapse and the shift. This is 1, 2, and 3. These are usually they are independent, and you don't fix these degrees of freedom. They are in the ADM formalisms. They are Lagrange multipliers. So now the problem we will have, you will see this problem in the 2 or 3 more slices. The problem we have is that we have these degrees of freedom. They are independent in the bulk. They are Lagrange multiplier, but at the boundary, or on the boundary, they are related. So this is what just said. So let me introduce now the Hamiltonian, or the action in the ADM formalisms. Taking the Einstein-Hilbert action, when you do the calculation, you find this. This is not important. You don't have to care about the form of the Hamiltonian. This is the momentum, but it's not important. What is important is what is in red. This is the extrinsic curvature of the boundary. This is not my Hamiltonian. No, you can find this Hamiltonian in this paper. But now you want to find the equation of motion. The equation of motion, when you have to take the variation with respect to h, n, and na. But what about the variation of these degrees of freedom at the boundary? No? Because when you take the variation in the bulk, these two are independent and you get the usual Hamiltonian constraints, which is H in the bulk. However, you can't freely vary these two fields at the boundary because they are related. Remember the relation I showed you, this one here. They are related. So for taking the variation, okay, you can take the variation, but you have to take into account this relation. You can introduce this relation using a Lagrange multiplier if you want, but you can also use a parametrization for this relation, a parametrization that solves this equation. There is a minus here, you can parameterize this equation, or you can find a solution to this equation using this parametrization here. You can say that these two degrees of freedom now depends only on these degrees of freedom, this one here. I put eta because you find later that when we use the metric I showed you, you find that this eta, or this field that you introduce here, is exactly this eta that you introduced at the beginning. So the action, now the boundary action, takes this form. And now you can take the variation without any problem, no? Because now you are using the real degrees of freedom on the boundary, which is this one only. When you take the variation, you find the boundary equation of motion. But let me go back for a minute and see something. Remember that I present you the action and the Einstein equation. From general considerations, you get this equation. This is a bulk equation, no? There is no boundary equation here. So why in the ADM parametrization you get the boundary equation? Something is wrong, no? Because actually, no, there is nothing wrong here. When you do the counting of the degrees of freedom, you find that the degrees of freedom are correct. What is this? So actually, when I was doing the calculation and I found this equation, I said, okay, this is wrong. I have to stop here. But then I realized the only way that this is consistent with the Einstein equation is that this is automatically zero. No? This is zero. Like, this is not exactly zero, but when you solve the Einstein equation given by this equation or given by the equation coming from the ADM formalism, when you evaluate this equation on a classical solution of the Einstein equation, you find that this equation is zero. This equation is an identity. So you solve the Einstein equation, but you don't have to solve this equation. Automatically, this is zero. I mean, this isn't okay. Automatically, this combination is zero. Yeah. Okay.
Sorry, can I ask a question?
Yes.
Yeah, is it zero because there is any nether identity associated with some gauge invariance?
Because of what? Sorry.
With some gauge invariance?
Yeah, somehow this is because you are you have the remaining of the diffuse you are allowed to do on the boundary.
Mm-hmm.
Then you solve the equation of motion, but still you have this freedom on the boundary. But when you evaluate this equation on a particular solution or a classical solution, a particular solution of the Einstein equation, you find that this is zero. So you don't have to solve for this equation. You don't need to solve this equation. So this is not a constraint equation for the Einstein equation. And this way, this is compatible, no, with the fact that from general consideration, even in this manifold that we are considering, there is no boundary equation.
Excuse me, I
Yes.
still don't understand completely. Look, you have some degrees of freedom at the boundary, right?
Yes.
You have some constraint which fits a part of the degrees of freedom, right? So some functions, and you vary over another function.
Mhm.
And so you get some additional boundary conditions. So the number of functions that you vary by definition by the function. Number of equations. So what can be wrong?
This is not exactly like this. No, here you have 10 equations.
Yeah.
No.
Yes.
But okay. The degrees of freedom in the ADM formalisms are and the lapse, the shift, and the 3 metric. You take the variation with respect to this, and you get this equation, which are constraints,
Yeah.
and you get the equation. This system of equation is equivalent to this.
Yes.
However, by doing this, you get this extra equation.
This is not the equation.
No, this is not the boundary condition. This is the equation. I got this equation from the. This is the action, no? Yeah. And now I want to take a variation with respect to these fields, no? You take the variation M of this field, and you get this equation. But for getting this equation, you consider only this part of the action, yeah. Not this part. Wow. Exactly. But still, you have to take the variation of these fields because they are not fixed. They are not completely fixed, no?
This is a question.
No, the boundary condition are this one here. No? These are the boundary.
Okay.
Exactly. So you have a remaining. Exactly. But you may think that this is not compatible, no, with this, no, because as I told you, no, from general consideration you don't get any boundary equation, even this manifold, this kind of manifold. However, here in the ADM formalisms that you take a particular parametrization of the metric, no, because here you are taking the variation with respect to G mu nu. Mm-hmm. Without any gauge symmetry, you don't get this equation, because if you fix completely this, you don't have to care about the variation of the boundary action. However, if you fix these degrees of freedom completely, you are over fixing, no? Is that clear or?
Yeah. So you fix those quantities.
Mm-hmm.
These are no.
Exactly.
And variation.
But exactly. Which is an identity. Yes. Okay. When you evaluate this on a particular solution of the Einstein equation. Let me tell you one more thing. This is not, I don't want to fix this because I want, no, it's because I'm using the boundary condition which are physical, no, that you fix the 3 metric. If you use a different boundary condition, maybe you will get something different. But I'm using this particular boundary condition, which are the ones that are physical, no, in the sense that, I mean, the only that we can fix is the 3 metric. You can fix the normal derivative of the metric, but this is, okay, what is the normal derivative at the end of the universe, no, of the metric? Or what is the normal derivative at some initial slice? This is, but if you use this, for instance, this boundary condition, you don't have to care about this. I mean, maybe you get some different equation, maybe this is not a constraint, I don't know. Yes.
Please use a microphone for questions. It's impossible to hear anything via Zoom. There is a microphone in the audience.
Is on? It's not working.
So you can
Okay, please. Okay. Yes, but I'm deriving this equation from the Hamiltonian formalism, which is the first order. Please repeat the question. It's not for me, it's for the.
Yeah, so this equation, you have to show the slide with this
Yes.
new equation that you have derived.
This
Yeah, this one. So you see this equation moves on the first order derivative.
Yes, but this equation is defined only at the spatial boundary.
Yeah, of course, of course. And how universal this equation actually follows from the Einstein equation enforced inside the bulk. Because you see, there are some additional structures. For example, this theta angle. It would seem that there are some parameters that bring additional.
But this is not because I want to bring these parameters into the game. This is because they are needed, or this one is needed in order to have a well-defined variation problem, no? Variational problem. Okay. You need this parameter in this particular manifold. Otherwise, you don't get the Einstein equation.
So can you write down some type of equation which would look like some projection of Einstein equations taken at the boundary would coincide with this one?
I'm not sure if this is a projection of the Einstein.
But then how this follows from that? You see, the only way that they are somehow proportional.
I mean, when you, okay, maybe we should go back.
Or this is a special type that when you have only asymptotically flat boundary.
No. This is in general. This is in general.
Absolutely.
This is in general. So these two functions are any function. So you fix the 3 metric on the boundary, and you have to fix this, and of course this one also. But okay, maybe the answer of your question is in this part of us. The point is that in this particular manifold, you fix different degrees of freedom. So on these boundaries, you fix this, which are this, and this. However, on this boundary, you fix this, which is a combination of these two parameters, and you fix this, which is a combination of the other parameters. So they are somehow entangled, they are mixed at this boundary. These degrees of freedom you are using, this is a particular problem of the ADM parametrization, and we want the ADM parametrization because we are doing canonical quantum gravity. Maybe in a different quantum gravity, you have.
I see. Then of course you can write a kind of a relation, that this is a kind of projection.
Maybe, yeah.
May I also ask something naive?
Yes.
Just to understand the relation with literature. So why? So what you are doing? It is very similar to what they call gravity on manifolds with corners, right? Because you have like
yes.
But
I mean,
is it
similar in the
these
sense-
corner contributions and edge modes? These are the same story in different language. Just to understand the relation with literature.
Yes.
Okay, thanks.
But when you do quantum field theory or quantum gravity in this manifold with corners, which is this particular case, sometimes you don't fix, you don't use these boundary conditions. You use a combination of the extrinsic. What is the variation? Sorry. Okay. You use a different combination. You don't fix the 3 metric, and sometimes what people use is this equals to some energy momentum tensor on the boundary, and then you don't care about fixing this. What I'm doing here, I am following strictly the physical idea that you fix only the 3 metric at the boundaries. If you put some matter or if you put some brain at the boundary, instead of fixing this, you can fix this. You can say that this is equal to some energy momentum tensor, and you have to add this term to the Einstein equation. Usually in ADS CFT, you do this, no? But here I'm using this boundary condition, that you fix only the 3 metric at the boundaries. Is that clear?
More or less, thanks. Yes.
Okay. Now I said that the fact that you have a boundary equation is compatible with the Einstein equation, because when you solve, not these equations, when you solve this equation, which are the equations derived from the Hamiltonian, when you solve this equation and you plug this solution here, this is an identity. So this is not an extra constraint for the classical equation. However, you have these degrees of freedom. This one, you have this eta on the boundary. This is why when you go to quantum gravity, the situation is different. It's different because in quantum gravity, you have to integrate the fields that you vary in the classical gravity. And in quantum gravity, you integrate this, and this, no? In the bulk. However, now in the boundary, you have to integrate the degrees of freedom that remain unfixed. And now you have this extra eta at the boundary. So when you do the path integral, you will have at the boundary is at the boundary with an extra delta, this extra delta with these two conditions, no? Imposing these two conditions. Or you can forget about this delta, and instead of integrating this, of course, in quantum gravity, I don't know what is the proper measure of the space, no? But regardless this, you can forget about this delta and these degrees of freedom, and you can integrate only at the boundary these degrees of freedom, this one, eta. But remember, no, eta is a parametrization of the combination of n and nr, which are Lagrange multiplier. So eta in the end is also a Lagrange multiplier. And the integration of this Lagrange multiplier leads to a constraint. In the same way, the integration of n and na in the bulk leads to the Hamiltonian or Hamiltonian constraint and the momentum constraint, or the Wheeler-DeWitt equation. So this is exactly what I said. No? When you for going to quantum gravity, you have to define the wave function. The wave function is defined in the usual way and as in quantum field theory. or the wave functional. And this is the action that we have with the boundary terms. No? Now you have to split this in these two terms. I'm using here the momentum, or the momenta, because I am in the Hamiltonian formalism. So I have to integrate p's, and then I have to integrate the metric degrees of freedom, that now they are parameterized by these fields. So remember, this is a path integral. So this is point by point at the manifold, including the boundary points. So when you integrate in the bulk, you have to integrate also these two fields. And when you do the calculation, this is I think it's well known in this area of quantum gravity. The integration of this field leads to the Hamiltonian constraint or the Wheeler-DeWitt equation. And this is because this is the reason why there is no time, because you are integrating the metric eta n, sorry, goes with time. So by integrating over all the n's, is like you are putting all the times at the same footing. So,
can you remind in terms of other?
Yeah, okay. I can remind you this, but remember that now we are in the Hamiltonian formalism, and now eta is an independent degrees of freedom. Now eta is not related with the other, with the original definition.
So you mean this eta is not related to n and na?
No, it is. With this one, no. With this one, no.
Yeah, but look,
because in the
they should somehow reach the limit.
Of course, yeah.
The space-like surface and the limit.
Yes. Yes.
Here they should.
But remember that this is a path integral, no? You are integrating point by point at the manifold, no? So these two are independent on the bulk, but when you touch the boundary, these two are related. And this is why I split this in two integrals. Here I can put these two fields, and I can put a delta. No?
Well, we want to say that here with Lagrange multiplier, you are integrating this continuous part, right?
I don't understand why. No.
Well, because there is a difference in plus integration.
There is an
integration over the coordinates. Integration over the net.
Exactly. Yeah, you're right. But
it's continuous. So the same.
Exactly. This is why we introduce this field, to take into account this, because again, I don't have space here to. Again, no. N and NA, they are independent in the bulk. There are two Lagrange multipliers or 4 Lagrange multipliers, and they are independent. But with the boundary condition we are using, as soon as you touch the boundary, this and the first component of this, they get mixed. So this is why this is at the boundary, and this is in the bulk. You can keep this expression here if you want, but here you have to put the delta. This is as you like more. No? You can introduce the delta here, imposing the boundary condition you are using. But I choose to parameterize the boundary condition in this way. And why I want to do this? Because it's easier, of course, no? Easier. And this assumption here, no, we are assuming that the measure is invariant on the translation of N and NA. This assumption is the one that leads to these two equations. This is an extra assumption. It's not extra. Okay. This is, you can derive this assumption from the first one, that it is also invariant on the translation of eta. And this is because in quantum gravity, the normal, let me just say this in a different way. This is just because this is an independent degrees of freedom. You integrate from minus infinity to infinity. You are integrating from minus infinity to infinity, so the action should be invariant under this on the translation of this field. Just you change variables and the action remains the same. But by doing this, okay, this is not important. This is just a rewriting of the action. Now you have the Hamiltonian, the action written in the Hamiltonian form, and also the boundary Hamiltonian written in this way. But this is not important. What is important is this part here. Yeah, H bar. Yeah, it's first order in P, and this is not my result. No, you can find this result in the Hawking paper that I showed you at the beginning, and the Hayward paper also. But remember, no, we are integrating the path integral. We are integrating also in eta, and we are assuming that the path integral is invariant on the translation of this field. This part here is I mean, for those who work on quantum field theory, maybe this is familiar. This is how you derive the bond. Actually, not quantum field theory, even in quantum mechanics. You take the variation of the wave function by pushing the final surface a bit in time, and you can identify here all these that I want to show you, the Schrödinger equation. For instance, the one that is the variation, the part of the variation that is related with time will lead to the Schrödinger equation. Or for instance, from this variation here, you can get these relations here, which are the ordinary ones in quantum mechanics. No? You take the variation, or in quantum mechanics, you take the derivative with respect to x, for instance, the space of the wave function. This is the wave function, and you get that this is the momentum. This is how you identify the momentum operator in usual quantum mechanics. Okay, here you can do the same. And again, this is not my result. No? In the end, my result is the identification of the boundary equation and the consequence of this equation in quantum mechanics or in quantum gravity. Because what is the procedure here? Here, t is not a physical time. T is just a variable. You have to identify the physical time, and the physical time is the proper time, or the proper space, or the proper shift. By identifying the physical time in this way, now you go back to this equation, to this relation, and you find these equations. So if you take the derivative of the wave function, or the wave functional with respect to the physical time, you get the Schrödinger equation. This integral here is because it's not a one-dimensional problem. No? It's a three-dimensional problem. And by taking the derivative with respect to space, you get this equation, which is, here I have to add one more thing, which is this. Remember, no? On the other hand, the wave function also contains these two integrals. And as I already said, if I take we are integrating in different words. We are integrating from minus infinity to infinity, these two fields. So you can change variables, and as we are assuming that the path integral is invariant on the shift of these variables, the path integral remains invariant, and you get this relation. This is nothing but this is the quantum counterpart of the equation of motion with respect to this field. When you have, this is again usual in quantum mechanics, no? You have some degrees of freedom, and when you go to quantum mechanics, all the relation that you had in classical mechanic now they are valid, or they are true inside the path integral or inside the brackets. So when you take the variation with respect to this field, you get the Hamiltonian, and because of we are assuming that the action or the path integral is invariant with respect to this field, this expression vanishes, and you get this relation here. You can pull out this Hamiltonian here using, again, this is ordinary quantum mechanics, so we are just applying this to quantum gravity using this relation. Here, there is a problem of ordering as in quantum mechanics, no? But when you find, if you find P, you can replace P for the derivative with respect to the corresponding degrees of freedom. And this is why you can pull out this here, and then you get the Hamiltonian operator acting on the wave function. This is the wave function. However, because of this condition, this is 0, and because of this condition, this is 0. So this implies that, let me go back to this equation. Remember, no? The time derivative with respect to this time is this. However, using the constraint, you find that this is 0. So this equals 0. This is why there is no time evolution in quantum gravity. Or in quantum gravity, in the bulk, because now we have one more equation. Oh, I forgot to tell you something about this. This is in the bulk, and this is the bar quantities are defined on the boundary. So this is the boundary equation, the Schrödinger equation for the evolution of the wave function. If you have this, see, what is important here is that for these quantities here, you can't do the same trick. You can use the same trick as I used before, that you can pull out this Hamiltonian from here. So this is a sort of Schrödinger equation, but this is not the usual form of the Schrödinger equation. This equation was presented in the paper that I showed you at the beginning by Harvard. And again, no, in the bulk, you get that there is no time evolution. However, on the boundary, you get that you can time evolve the wave function. But we have one more thing. We have this field, no? And now we can use the same argument. The wave function should be invariant on the translation of this field. You shift this field, and the wave function should be invariant because we are integrating from minus infinity to infinity. So by doing this, you get this equation. This is the quantum counterpart of the classical equation of motion that I showed, the boundary equation of motion. The point is that here this is not an identity. because there are no classical solutions. So here you cannot evaluate this relation on a particular classical solution. Now you are integrating over all the solutions, classical or not, no? All the configurations. This configuration could be solution of the equation of motion or not. So now this is a constraint. Quantically, this equation is a constraint. Okay, here you can read, I put it. Or this is a constraint. When you put this constraint at when you specialize this equation, this constraint at the final slice, you get this boundary constraint, which together with the boundary Schrödinger equation rules the Schrödinger evolution of the wave function in quantum gravity. So before this, before my work, if you wanted to evolve the wave function in this kind of manifold, you use this equation. Again, this is not my result. What I'm saying is that in addition to this equation, you have to take into account this equation. This is the main result of the paper. This one and the classical one, no? And the proof that actually this is an identity, no? And there is no contradiction between the Lagrangian and the Hamiltonian formulation in this kind of manifolds. So, questions? Please, yeah, let's discuss, because I know that this is
have an impression. Okay, so you kind of fix the trivial boundaries, and the remaining degrees of freedom boundary are kind of, yeah, I have the impression that they are kind of gauge. Is it true? So you have a four metric, it has more.
Yes, somehow they are gauged in the same sense that these two are gauged.
Yeah.
Yeah.
Yeah. So you eat some of the combination. So this is kind of big gauge transformation of the change eta. So you change the vary eta, and you get some non-trivial equation. So I wonder, how does it happen that you kind of gauge transform metric into another coordinate system? This is kind of changing eta, is kind of gauge transforming the metric, and somehow you get the equation. How does it happen?
Okay, the short answer, I don't know, but but the same happens in the ADM formalisms. No? You can change coordinates on a particular slice, no? But you are breaking the diffeos when you take this. And this is because you have two boundaries. Now you have this boundary that breaks more diffeos. But there is one remaining, no? There is a freedom.
Yeah, what happens in ADM is that if you throw away equations which are obtained with variation with n and I, okay, lapse, you still get equations which kind of derivative of the equations which are obtained with respect to variation of n and a. So you're not kind of.
No, they are independent. No, you mean that the equation coming from here and from these these 4 degrees of freedom are somehow related with this equation?
Yeah.
No, they are independent. They are completely independent. This is why this system is equivalent to the Einstein equation. No?
Suppose you have equation time derivative of h equals to 0 and time derivative of j equals to.
Okay, time.
I believe that they are the consequence of the equation below. No?
No, if you, but
the equation below
okay,
is the second order equation.
Let me take, if you have if you had this case, this equation will not be a constraint equation,
Yeah.
but they are constraint equations, no?
Look, you have 9 equations in below, okay? So
Here,
yeah,
6.
equations for HAB, okay? Right?
6 equations.
Okay, 6 equations for HAB, and because HAB and is, yeah, so you would have an extra 4 equations for 6 variables.
But I'm sorry.
Unless these equations are interrelated, right?
I'm sorry, I forgot to tell you something. No? In addition to these equations, you also have these equations. I forgot to tell you this. No?
Okay.
This is because this is Hamiltonian. No, you have to take the variation with respect to.
Yes, but still, you have extra 4 equations, and of course, they are related to the.
No, they are independent. This is, I mean,
independent. You would have 10 equations for 6 variables.
Okay, maybe we are talking 2 different things. No?
Yeah.
There are 10 equations.
Yeah.
No? 6 and 4.
Yeah.
And you, I mean, by doing combination of this equation, you don't get this equation.
By taking the derivative of the equations above, you get the consequence of the equations below, of course, because they're like, they cannot be independent.
Okay, we can do it. We can say it in the different way. I'm somehow easier in Maxwell theory.
Yeah.
You have 4 degrees of freedom.
Yeah.
But 2 of them are gauge. No, they are only,
Okay.
they are not physical degrees of freedom.
Okay.
But from these 2, you don't get these 2 equations.
So you have Gauss law, okay?
Mm-hmm.
And Gauss law is
It doesn't.
an extra
It
equation,
doesn't.
okay?
Yeah.
In gauge A0 equals to 0, okay? But this Gauss law is not independent of the other equations. If you take a derivative, time derivative of the Gauss law, this is the consequence of the equations. You don't get, yeah, you know, yeah.
Okay. Show me this how to do it, but I'm not sure that.
You never get more equations that there are variables, right?
Of course, yeah.
Yeah, so you have 6 variables here, the equations below.
Mm-hmm.
You can solve them, solve the initial problem for HAB
Mm-hmm.
and phi AB. Okay, 6 plus 6.
Okay, yeah, you can solve this,
Yes.
and you will find a whole spectrum of solutions. But from the solution of this equation, now you have to pick the ones that also satisfy this equation.
So you can impose this constraint only at the initial time, right?
No. This constraint, I mean, we are talking in the usual ADM formalisms.
Yeah.
No, these constraints are defined on the, because the variation this is in the bulk, no?
Suppose you specify the initial conditions, HAB and phi B at the initial time. Right?
So at the initial time,
so that these constraints are satisfied.
yes,
right?
yes.
The
But also at the initial time +1, +2, +3, plus and at the final time. You have to.
Suppose you start with the initial time t equals to 0,
Mm-hmm.
some coordinate system, so that these constraints are satisfied only at the initial time.
No.
Suppose.
Okay.
You have this Hershey data.
Mm-hmm.
So you throw away these constraints and you solve the equation.
Mm-hmm.
Because there are exactly the same number of equations.
Exactly.
And you get the
Yes.
and it automatically satisfies
But
the
okay,
constraints
but
anytime.
you are solving what you are saying, that you are solving at the initial time, no? And then you have to extend this solution to another time.
Yeah, but you don't need constraints to extend it. So the
But
constraints
when you
are
take-
related to equations of all.
When you take the variation, I mean, for deriving this equation, you take the variation of the action. Let me do it.
So
The variation of the action at any time, not only at the initial time. Okay, maybe we can discuss. Okay. Okay, these are the conclusions, and this I already said this. There is one more point that I want to discuss, and this is this one, because before my work, you had the option to evolve the quantum state using the quantum Schrödinger equation, the boundary Schrödinger equation. But now you have the Schrödinger equation plus this additional constraint. And the question is now, using this constraint, we will have solution of the time-dependent Schrödinger equation, similar what happens in the bulk, no? That you have the full Schrödinger equation, but as you have two constraints, the Hamiltonian constraint and the momentum constraint, you don't have a time evolution. So, is this the case here? In this case, there is not really time evolution even at the boundaries, and even if you take the boundary to infinity. This is a question that I don't know how to answer yet. Okay. Just to finish this, I don't know how to solve this equation. In 4D, I don't know how to do it. This is impossible. Like we don't know how to solve the Wheeler-DeWitt equation. However, in 2D, I'm working on this now. In 2D, there is a way, we can solve this equation. In 2D, this is an ordinary one-dimensional equation or constraint equation, and the boundary, the Schrödinger equation in 2D is also, there is a way that we can solve this equation. Actually, yeah, in 2D, let me clarify this. In 2D, in JT gravity, which is easier, or probably the easiest. In JT gravity, there is a way for solving this constraint. And okay, maybe in 2, 3, 4 months, I will conclude this. In 2D is not exactly what we want. We want to study real 4D gravity. Okay. Questions?
Are there any questions?
I think there were a lot of questions already.
Maybe there is still some.
Can I just ask something? So you say that in addition to the Schrödinger equation, there's another constraint.
Can you just speak louder a bit?
Yes. Can you hear me?
Please.
So you say that in addition to the Schrödinger equation, you have another constraint, but
Yes.
At the beginning, you said that this constraint follows directly from the bulk Einstein equation. So why do you expect this to be another constraint here? I mean, I don't really.
At the quantum level, not in quantum gravity, this is a real constraint because of this assumption, no?
Sorry, I don't see what you're pointing at.
I mean, your question is that, can you repeat the question?
Okay, maybe another way to say it is that, is there any way in which this constraint would be automatically satisfied at the quantum level?
The quantum, sorry, what? I can't hear.
Are you certain that this gives another constraint, or can it be that in some way it's automatically satisfied in the same way?
No, exactly. No. I think I said that, no? Classically, this is the, without this integral, classically, this is the equation. Without the integral, this is the equation, classically. And classically, this is an identity when you evaluate this relation on a classical solution, on a particular solution of the Einstein equation. However, at the quantum level, there is no classical solution. You are integrating over all the configurations. They are classical, this configuration could be solution of the Einstein equation or not. This is why this is not an identity, because this integral here you are integrating over all configurations. And this is why this is an identity. Sorry, this is a constraint. Now you have to solve for, so you have to satisfy this constraint in order to evolve the quantum state. Is that clear?
Okay, thank you.
Questions?
You had that like extra equation of motion at the beginning.
It's this one,
Uh,
without,
the one that you said that follows from Einstein equation.
I mean, from the Einstein equation,
Yeah, the very first one that you said that follows from.
from the, I mean, the Einstein action, Hilbert action. You get the usual Einstein equations.
You said you have some extra equation, which is a kind of a puzzle unless it follows.
Okay, let me go back.
Just a couple of slides.
This
Yeah,
one.
this one, yes.
Okay, this one. Let me.
Yes. No, the question was whether can you write it in the covariant?
That's a good question. Yes, it's possible, but it's harder. No, I mean it's more complicated because here I'm using that the boundary is at the constant value of some coordinates. I'm using this particular coordinate for doing this. For writing this in a covariant form, actually I have the action here. You have to derive this action from, I mean, this equation from this action. No, see that in the non-covariant form, I have only end and NR, but in the covariant form, I have the three ends. So here I have only one P, which is the 0, component of this tensor, the momentum. But
Well, I don't know, it's like too many like technicalities, but I would expect that
you can do it.
should be
You can do
possible
it.
to do
Yes,
it like
yes.
in the coordinate stream.
It's possible. But again, no, it's harder. I mean, the manipulation of the equations.
Any other questions? Okay. Thank you for the talk.
Thank you.